Okay, so I think this is where we stopped yesterday. Those are the Kalman filter equations. Can you turn on the lights, please? Or the... Oh, actually, I know where to do it. It's here. Perfect. So, the Kalman filter equations are over there. The ensemble Kalman filter equations are over here on the screen. Basically, they're identical, except that now it takes index I. I have dropped the time index here. There should be a T everywhere in this, but the time index is gone for now. We will assume that this is a function of time, and the prediction equations. So this is the update step. The prediction step is something I have not written down. If you are not sure what it is, please remind yourself from Varun's lecture what the prediction step of the ensemble Kalman filter is. I have not written that down here. So this is just the update step, and this is the update step for the ensemble Kalman filter, yeah? So you can see that they're basically identical, and the idea is to now try to see how to actually implement this and what its properties are, and how does it represent a probability distribution that we want it to represent, and so on and so forth. So that's the aim for today, yeah? Instead of starting with these equations and then deriving the way to implement it and so on, here is the notebook which I had sent to everybody. I had sent it on Slack channel. I don't know if they check Slack or not. Did you get the notice? Wait, I need to know what happened to Slack.
Or they can download it now.
You can download it now. It's on the Slack channel. So. It was, the window was open. I closed it just now, but was it this? No, not this, not that. Okay, I don't know where it went. It's loading. Okay, so it's this, there is a collab link. So this is the collab link, and my laptop had suddenly become extremely slow. Just hold on 1 second. Oh, Zoom is taking up all my memory. Okay, anyway. So this is the, oops, sorry, it's very, very slow. It's taking long time to, okay, anyway, so this is the collab link. I guess you have this channel, yeah, right? I'm not going to, okay, are you able to access the notebook? Yes? Okay. How many of you are able to access the notebook? Raise your hand high up. I can't see if you don't. Okay, so about a little more than half. So I'll wait for some more time.
So there are two notebooks.
Yes. So the first one. So there's two collab links. Not the one that says Lawrence 96 system. The one that says the one that doesn't say Lawrence 63. The one above. The first one. The first of the two collab links. Okay, you have to be enthusiastic either to do the algebra and the maths or the programming, ideally both, but one of the two for sure, minimum. You can't be unresponsive for both the mathematics and the programming. Then you're not really doing anything at all. So, one of the two, yeah? Are you? Are you able to access this? Who is not able to access it? Can you please raise your hand so that I can come and help? I told you, work in teams of 2, ideally. So somebody who is not able to access it, can you find somebody who is and ask for help? Okay, who is not able to access it? I need answers right now, like within 1 second. Who is not able to access it? Can you please raise your hand? Okay, who is able to access it? Please raise your hand. The sum is not equal to the number of people. Please. That not acceptable, completely not acceptable. Yeah? So, those who are not able to access it, can you please raise your hands once more? Or not once more, first time nobody raised it. Wait, what's happening? The answer is very clear. You are able to access it or you are not able to access it. There are only 2 choices. I think for a yes or no question, if there is confusion, there's a serious problem. Okay, so here is what the notebook should look like, and I hope this is, where did it go? Yeah, here. So hopefully this is what it looks like. The colors may be different, but everything else should be the same. Yeah? Is that fine? Packages, forget it. I have no idea what JAX means. No clue. This was written by my student, and here is the credit, where it's due. Finally, it's here. Okay, so this is the person who wrote the notebook. He will be here around today for some time at least, if you want to talk to him. His name is Shashank Roy. He was a PhD student here. He just submitted, and now he has moved on to go for a postdoc. So this ENKF was written by him. All the mistakes are what I introduced. When he gave me the notebook, it was working. I managed to break it, but anyway. So, coming back to the notebook, right? First is just importing some packages. The delay is a lot of delay. What I see here is what I see there after maybe a few seconds. So I will have to make sure that I take care of the delay. This is a way to solve differential equations. So what this is too long, okay? I'm going to trip on this wire. Okay, so all of you have at least seen the Lorentz equations somewhere, even if you may not have solved them. Have you seen the differential equations that are written over here on the screen? Yes. Yes or no answers, very easy to answer. Yes or no? Yes, thank you. Okay, so broadly they can be written like this. My favorite notation, which is x dot equal to f of x. X in this case is a 3-dimensional vector. Now the components are also unfortunately written as x, y, z, but I hope there is no confusion. So these are basically 3 differential equations, and we want to solve these equations. How do you solve the equations? Well, you can't solve them in continuous time on a computer. So you need to find the solutions in discrete time, which means that the solutions will be obtained at, let's say, time t equal to 0, t equal to h, t equal to 2h, and so on and so forth. So this will be called, okay, maybe I shouldn't use the word h. H was observation operator for so long that, I don't know, delta, 2 delta, and so on and so forth. Delta is the time step for solving the differential equation. So the solution will be available only at these times. And that little thing called solver, basically the time step here is that delta which I wrote down there. And x initial is the solution at a time at, let's say, so the x initial is like the solution, say, at x of t, and the solver gives you the solution at x of t plus delta. the solution at t plus delta. That's what the solver does. If you don't know anything about Rangekatta methods, this is RK4. If you don't know what RK4 is, that's perfectly okay for now. We don't need that detail right now. But it basically gives you this. It gives you a solution going from time t to time t plus delta. And you may want to, if you are taking observations, say in a time scale which is 0, say capital delta, then 2 delta, and so on, we may take multiple small little steps of size delta to get to the observation time. So this could be the observation times. And to go from one observation time to the next observation time, we can take multiple small steps of the differential equation in order to reach from one to the other. And that will come later, but the solver is what, yeah? Okay, so this function simply, this cell simply defines the right-hand side, which is 10 into y minus x, x into 28 minus z, and blah, 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 dot, 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 and so on and so forth. The model dimension is 3. It's a 3-dimensional ODE. The parameters that are needed are defined here. These are the standard parameters for the default parameters for Lorentz equation. And the model is called L63. The function is called L63, Lorentz 63. And then the details here are not that important, but effectively this function called generate trajectory takes in a initial condition called XO, some point in the 3-dimensional space, solves the equation for a very long time, and then takes the last bit of it as the actual trajectory of interest. The reason for that is, I showed you this picture of what is called the attractor. So the Lorentz solutions after a very long time will belong to something that will look like a shape that looks like the Lorentz attractor which I showed in the lecture last time. But if you start from somewhere far off, what will happen is the trajectory will kind of take some time, it will do something, 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 eventually will come very close to the attractor. And so what we want to do is to work with trajectories that are on the attractor for reasons that I will not get into right now, but we can discuss those later. But that's why so you start with some random initial condition, you go forward in time, the initial part is kind of thrown away, and the last part is what is considered the trajectory of interest. So that's what this function does. I'm not going through the details of line by line the code. I'm just giving you the broad overview, and hopefully once you read the code, things will be clear what it does. Okay, so random number generation. When you generate random numbers on a computer, they are not really random, they're pseudo-random, in the sense that they take something called a seed, and if you give the same seed before starting to generate random numbers, that is called the initialization of the random number generator. And once you initialize it with one seed, you get one sequence of random numbers. If you initialize it with a different seed, you get a different sequence of random numbers. If you go back and initialize with the first seed again, you will get the same sequence of random numbers. So that's the sense in which they are not random. That is, by fixing the seed, you actually generate the same sequence of numbers. So that's why they are called pseudo-random. What is random about them is that the distribution, the statistical distribution of these numbers over a long sequence of these numbers will have properties of the distribution of interest. So if you want to get 10,000 random numbers from a Gaussian distribution, whether you start from seed equal to 3 or seed equal to 7, you will get a sequence of 10,000 random numbers. Both of them are different, but the distribution will be close to each other. Not identical, of course, but close to each other. And again, if you start with the same seed, seed equal to 3, you will get the same sequence of 10,000 numbers, but of course the distribution will still be Gaussian, for example, if you want to get Gaussian distribution or uniform distribution or whatever other distribution you want. So the seed is a way to get reproducible results even from after having generated random numbers. Sorry, not after having. If your code uses random numbers, but you still want reproducible results, you can set a seed, and after setting the seed, if you run the same sequence of steps, then you will get identical results. Except the following. Python, when it changes versions, it will change small details of how random numbers are generated. So Python version 3.3 and Python version 3.7, even after setting the same seed, will not give you the identical results. There is that unfortunate part, which is that if you want really, really identical results, you also need to preserve your Python installation to be the same exact packages, the same exact version of each package, and so on and so forth. It's just tedious, but science is tedious. Okay, anyway, so,
Please, one more question.
yeah.
How to decide distribution, which distribution we have to follow while generating the random numbers? Is it based on our data?
Defined by the problem. So we have been dealing largely with normal distributions, right? Gaussian distributions. What do you mean? So this is too generic a question to be able to answer. Give me a problem and I'll tell you what to do. Or I will discuss with you. I may not know what to do, but anyway. This question is not very, it's like saying, how do you solve a physics problem? Well, I don't know, give me a problem, then we can discuss a problem. Right? So what distribution to use? What is the problem of interest? Okay, so in this case, that multivariate normal is just a choice. It can be uniform, doesn't really matter at all. And why random initial condition? No good reason. It can be, it could have been a fixed initial condition. Anyway, whatever. But the idea is that we want the solutions on the attractor, and hence we solve the differential equation for a long time, and then start using. So this function called integrate forward here will take you forward in time, and so on and so forth. Yeah. Okay. After having done this, then we just call the function to generate the trajectory. So that will give you a long sequence of points which are essentially the representation of solution at time 0, at time delta, at time 2 delta, and 3 delta, and so on. The delta is the variable called time step, or now it's just called dt. So the dt, the variable dt there is that time step, the delta that you have. Yeah? Okay, so for whatever setup that was here, I haven't run this, so none of the packages are loaded. Just give me 1 minute. Done, loaded, define, okay. Define the function, and now I just call the function. So this may take a little bit time. Trajectory is not defined. Oops, what happened? Okay. So yeah, so that gives you a long sequence of basically that is supposed to represent a solution, and this is just a plot of that. The horizontal axis is the horizontal axis is time. I have not labeled anything, and the vertical axis actually represents all the 3 variables. So one of them is x, the other is y, the third one is z, and this is the solution. Yeah, you can plot, for example, something like that by using the 3D plotting or even 2D, for example, right? Okay, so that's the trajectory of interest that we'll take as the truth. The atmosphere, this is our atmosphere. That's what we want to observe, and without knowing the initial condition, we want to try to follow that trajectory. So this kind of setup is called the identical twin setup. Identical twin in the sense that you generate a trajectory, that's your truth that you want to try to estimate somehow. And now we can generate observations, and using the observations, we want to go through the assimilation process in order to get the probability distribution that will give us an estimate of this truth. So we are not supposed to have this truth with us, But of course, numerically we do have it, and hence we can compare how good or bad our experiments are. Yeah. So that's identical twin setup. And so what do I need to do? I need to generate observations, right? To generate observations, so this is just a function that generates observations by doing the following. This mouse is so slow that it's okay. Sorry, it's a bit too long. Okay, what I can do is put this into the new line. I hope that works. Okay, so now you can see it in one line, right? So the observations are, we have the full trajectory. The at here is multiplication, matrix multiplication. I'm flouting the norm that Varun put for me, put for us, which is do not multiply matrices, but I'm going to multiply matrices. And so you just take the observation operator, the capital H, for example, there, and H times the trajectory gives you basically the set of observations, but now they don't have a noise. So these are noiseless observations, which is the oxymoron I said yesterday, right? And so to that, we add a set of random numbers of the same size as the actual set of observations, right? So in this case, for example, if H, so remember the notation, so capital H is M cross N. In this case, N is equal to 3, the dimension of the system. M is the number of observations. In this case, in this experiment that I have set up here, M is equal to 1. So we are only observing one component. So this will be a 1 cross 3 matrix, basically a row matrix, right? And so at each time, we have one single observation. The number of observations is basically the length of the trajectory. Oh, that's gone out of the screen now. That was some 750 or something like that. So we'll have some 750 odd observations. So we'll have to add 750 random numbers, 750 Gaussian random numbers in the observations in order to get noisy observations from the known trajectory. And that's what this function does. Yeah? Okay, so that's the definition of the function. In order to use it, we of course define a observation operator. So capital H is the observation operator. In this case, one single observation, so it's 1 cross n matrix, m cross n, m equal to 1. That's np.0 is that H operator. Then you set, let's say, this is the second component. So the observation will be for the y component. Remember, Python is indexed from 0 onwards. So H 0, 1 means second index. So that means the second observation, the y observation. And the observational error covariance is set to be the identity matrix of dimension 1. Okay, that's number 1. And mu square is the observational error covariance, or mu is the standard deviation for the observational noise. And you add that noise, you generate observation. So that's this cell. So you generate observation. And now let's just plot it to see what that looks like. It looks like this. So the y component is plotted now, and shorter piece is plotted so that you can see it easily. But there are some 750 odd observations. And so there are these, so the trajectory is shown in green, the line is the actual true trajectory, the observations which are noisy and hence the dots are off. And using these observations of a single component, we want to be able to reproduce the full solution of all the three components without knowing the initial condition. That's the problem at hand. Yeah? That's basically what the data isolation problem is, right? Okay, so a bunch of parameters have been set up. They are not very efficient way of doing this, sorry. This could have been made a bit more efficient, but this is not the most efficient code per se, it's a working code. Okay, so I'll run it and then explain. Oh, sorry, I ran the wrong thing. Okay, so where was it? There. So, what are these parameters? Some of them are not very necessarily useful to look at. We have to run an ensemble Kalman filter. What is the process? We have an initial condition, which is the initial probability distribution represented by sample. And so we need to choose the initial ensemble. at time t equal to 0, we choose a set of initial conditions, and that's called an ensemble, right? English lesson, ensemble is a singular noun. Sample actually is multiple things, but sample is a singular noun. A sample consists of the full set of all their sample points. Same thing for ensemble. A ensemble consists of multiple ensemble members. You will see in many places and in colloquial language as well, samples as a plural, which is actually wrong in the sense that, okay, anyway, so that's part of the English lesson. Go back and look at sample in the dictionary. There are at least 3 or 4 different meanings. This is one of them. Okay, so the bias and the covariance. So here is the picture. We have, I'm going to draw the trajectory as, so let me erase this bunch, and this is R3. I have an initial condition at this point, and using it, you go forward in time and get a solution. That's the trajectory of interest. We don't know this. We want to generate an initial ensemble, initial set of a set of initial conditions at time t equal to 0, with which we start our assimilation step. So that may be here or may not be here. So the initial conditions may be chosen, let's say, from a Gaussian whose mean and covariance are to be specified, and that's what E bias and E cov do. So what E bias specifies is what is the total bias. So the mean could be here, for example, and the covariance could be a ellipse. In this case, it's actually a spherical, I take diagonal covariance, but it could be something like this. So the initial conditions will come from a Gaussian that is centered somewhere else. And this is what is called in the program the bias. And the covariance of this Gaussian is called E. Oh, so the E bias and E cov are these objects. So we may not start even from initial conditions that are anywhere near the true initial condition. They could be quite far. And in fact, it turns out that the way I have set it up, the bias is 10. So the distance between the true initial condition and the initial condition that we choose is on an average roughly about 10, which is quite large. So we really don't have a clue what the initial condition is for the ensemble, for the assimilation. Yeah. Okay, so how many observations, what's the dimension of the model, the gap between observation, that was the dt. Oh, sorry, the dt, wait, sorry, I made a mistake. dt in the program is the gap between observation, the capital delta, and the model, the solver time step, is the delta, the little delta. I messed up, okay. Capital N is the number of ensemble members, number of crosses that we want to choose. In this case, we'll start with 100 different initial conditions. It's ensemble of size 100. Alpha is inflation factor. I haven't talked about inflation. We'll come to that somewhere in the middle of the lecture. And the observational error covariance that we want to use, the number of assimilation steps, that's the number of observations, and so on and so forth. Yeah, is the set of parameters clear? Eventually, what I will ask you to do would be to play around with this program by changing certainly a few things. One is the size of the ensemble. So which parameter will you change in order to change the size of the ensemble? So the parameter n, capital N, which is 100 right now, reduce it, increase it, and so on and so forth. That's one thing. Of course, we can't change the time between observations and so on and so forth. That is all set by the model and observations. The other thing to change is the initial ensemble. So maybe you can decrease the bias of the initial ensemble or increase it and so on. Yeah. Okay. So and alpha, which is the inflation factor, I will come to talk about inflation, but you can then play around with inflation later. Yeah. Okay. So the rest of the code, these functions are basically the 2 steps of the ensemble Kalman filter: predict, update. or predict. That's called forecast. That's straightforward. What should it use? It simply uses the solver, because every ensemble member, every cross here will go through a predict step. So this will go to someplace there, this will go to someplace there, the solution to that may go there, and so on and so forth. So after taking one time step between the observations, so the time step delta, going from say 0 to capital delta, which is called dt in this case, each of these initial conditions will go to some other point. So I'll get 100 points at some other place, and that is the forecast step. Yeah. And then the analysis or the update, and that is actually doing exactly that. So let's just pay some attention to what it's doing. Row, I will explain what is the row in 45 minutes, 1 hour, something like that. I think 45 minutes. So forget the row for now. Think of row as equal to 1 right now, identity actually, not okay. So row, neglect the row right now. It's calculating the covariance of the forecast ensemble. That's the first part of that code. In the mathematical symbols, what's the mathematical symbol that corresponds to this part of the code? So I'll give you 2 or 3 questions at the same time. Think about them, and I will write something else in the meanwhile. So that's one piece, right? There is a matrix multiplication by something like this, which is transpose of H. And that variable is called PF transpose. Okay, I mean, now the variable names are going to give you hints exactly what to look for. But anyway, and then that is multiplied on the right-hand side by the inverse of something that's inside the parentheses. H multiplied by that same object over there plus R. Okay, so I think everything is identically parallel, so make sure that you look at the equations and look at this and see if you can make the one-to-one connection. I'll leave you, and we'll come to innovations and these 2 steps in just 1 minute. But while you're looking at that code, wait. Okay, in general, scientific computation should be that. You shouldn't start writing a code. You should think of an equation, think of an efficient way of translating the equation into a code, and then start writing the code. I started with explaining the code because, well, now we are going to understand what mathematics goes behind it. But so that's exactly what I'm doing actually, effectively, trying to explain to you how to translate that into that, right? And how do the equations on the board get translated to equations or the code, the variables that I used here. And the way this code is written, the variable names are actually identical to what is on the screen over there, right? So what is the highlighted bit here? The I said I forget about alpha for now, which is the inflation factor. I'll explain inflation in a minute, but for of forecast ensemble, which is the covariance, what's the mathematical symbol that I have written down in the equation over there? It's PF. It's a forecast covariance multiplied by, on the right hand side, H transpose, right? So that bit, that variable is exactly this little bit here. PF H transpose that's part of the Kalman gain. There is a PF H transpose that's also part of the Kalman gain. And the next line literally translates this into the code. The Kalman gain is PF H transpose multiplied by the inverse of H times PF H transpose plus R, which is the error covariance. Yeah? In our example, what's the dimension of the matrix that sits inside the inverse? So there is that linear algebra dot inverse, that's the inverse of a matrix. What's the dimension of the thing that's inside it? What's the dimension of this matrix H PF H transpose plus R? Sorry? The matrix of which we are taking a inverse. H PF H transpose plus R, it's the inverse of that. What's the size of the matrix that we are trying to invert? It's n cross n. Okay, that's one answer. We are trying to take an inverse, it better be a square matrix. There are only two dimensions on the board, n and m. So it's either n cross n or m cross m. Which one is it? It's m cross m. Should we do democracy or should we do maths? I don't think democracy is a good idea, so I will not take vote for m cross m, but it is R. What's the dimension of R? It's in the observation space, m cross m. What's the dimension of H? M cross n. So this matrix has to have dimension of m cross something. And then after doing all this, then it better be m cross m. So it's the dimension of the observation space. In this code, what's that dimension? In this specific instance, in the code that we are running. What's the dimension of that parenthesis? H times HPF H transpose plus R. It is not 3 by 3 because it's not n cross n. You're left with one other choice. M cross m, which is 1 cross 1, a number. So in this case, we are taking inverse of a number, that means 1 over that number. Okay, anyway, that's what it is, yeah? Okay, so in this case, it's easy to do. And then, it's multiplying the Kalman gain with what is called the innovations. What is that variable called innovation? The variable called innovation is the obs. There is a term that's written as perturb obs. So those are the observations. The observation y minus h times the forecast ensemble. So that's that hx, yeah? So it's literally translating this into the code. And of course, for an ensemble Kalman filter, I need to put a index I on each of these. That's basically what it's doing. For each ensemble member, it's applying this equation exactly as it is written over there. Yeah. Okay. So, and then it's just a you call the forecast analysis step in sequence for every observation time. That's basically the next step, which is yeah. Okay. I hope the code is clear. It's explicit translation of that mathematical equation into this, and so I generate. Oh, sorry. I guess I define the code. I generate an ensemble, and then the loop over here, the stored filter ensemble, is essentially just the loop of do the prediction. That's a forecast of the ensemble. Perturb observations. I'll come to that in a minute. So for now, just assume that that's a variable y. It is actually not y, but I'll come to explaining why it is not y in just a minute. And then use it in the analysis. So then you get an analysis ensemble, store it for future use, and then go back and call the ensemble as filter ensemble, and so the loop can continue. Yeah. So it goes for every observation time. You go through, you first predict to get to the observation time, do a update, go back, do a prediction, do a update, update, predict, forecast analysis, or predict, update, identical combinations of words, yeah? Okay, and that's it. So right now it's being called just, yeah, okay. That's basically, so I'm just storing it for future use as ensemble 1, stored ensemble, stored filter, and so I'm saving it for further use later. But this is the cycle that it's going through, yeah? Now, what do we want to see? So forget this part of it for now. Now we can actually visualize. For example, let's look at the X component. X component, which is not observed. And if I plot this, oh, I didn't run this part of the code, so that variable does not exist. Just 1 second. Run it. So this is the one that takes a bit of time, of course. And now I can try to plot. Oh, sorry, I ran it twice. Okay, so I ran it twice. I'll tell you why. And that, and okay. So what's plotted here is 3 things. Here, yeah. Now it is on the screen. This line here, thick line, is the actual true trajectory. The solution that we obtained that we are not supposed to know anything about. In this case, of course, we do, and we want to compare our actual assimilation output with that, right? So this is the true trajectory, that is the trajectory of interest, the truth of interest. I ran these things twice. So the ensemble Kalman filter was ran twice by choosing an ensemble that is this cyan color, the one in the middle, and the magenta color, which is the one on the top. 2 very different biases, for example. In one case, the bias was about 10 or something. In the other case, the bias was 20 or I don't know, 15 or something like that. So the ensemble members were quite distinct in both these cases. You start going through the cycle of predict, update. And what is the aim? The aim, at least at the minimum, we want to try to start capturing the truth. That is, the ensemble should come closer and closer to the truth. It's something that we want to do. Of course, the other thing that I mentioned, remember, that we may want to reduce the uncertainty in the ensemble as well. What does that translate to? If we want to, by the way, scientific computation has a previous step which I didn't write down, which is the science part of it, which is translating concepts into mathematics. But anyway, that's it. So concept, so we want to reduce uncertainty. What's the mathematical translation of that? What do you mean by, what is it that we would like to see being reduced as a desirable outcome of assimilation? Something else? Sorry. Say it loudly. I can't hear you. I'm terrible at lip reading. Some people are good at it. I'm not. So if you just say like this, I can't hear, or I can't read your lips. So please say out loud whatever you are. At least 2-3 people were trying to say something, but I couldn't hear it. So go ahead, please. The variance. Okay. So the variance should decrease. Or, for example, the trace of the covariance could decrease and so on and so forth, right? Okay. So, what does that translate to in terms of an ensemble? If you have a big set of cloud of points, which is representing a probability distribution, the reduction of variance will translate to, in a picture, the spread of the ensemble will decrease. So, in this case, for example, roughly, the spread of this ensemble, the width of this, by the way, so I didn't really very clearly specify what I'm plotting. Of course, the green line is the true trajectory. The magenta are actually 100 different lines. For each of the 100 different ensemble members, I'm plotting the trajectory. So there are 100 lines in the magenta cloud. There are 100 lines in the cyan cloud. Each of the 100 ensemble members is being plotted. So if you see a thicker spread, then that means the variance in that variable is high. If it gets thinner and thinner, the variance is smaller. Yeah. Okay. So, and you can see that the ensemble, in fact, both these ensembles, which are very distinct, quite different, are in fact coming eventually close to each other. So this is what I talked about when I said stability. Two different ensembles. I don't really care what they are initially. I don't know what they are. I mean, they're quite distinct. But after doing a few time steps of assimilation, both of them are quite close to each other. And hence, the choice of initial ensemble does not matter as much. If this property is valid, that is the stability, this is called stability. Stability of the filter. And if the filter is stable, then the choice of initial ensemble does not matter so much. Yeah? So this is an example of stability, basically. Okay, this is the unobserved component. What about the observed component? I think there was a plot. Yeah. Yes. Okay, so this is the plot of the observed component. Yes. Sorry? Qualitatively different or quantitatively different? Okay, so how about let me quickly go through this. Only two more steps left, and then you start running it and try to start interpreting what you're seeing. So when you run it, and if you get different things, if they are qualitatively very different, then we'll discuss why that is the case. Yeah. So let me just finish this one or two more cells of the. Okay, so this is the plot of an observed component, and because it's an observed component, now it's a bit messy. Why is it messy? Oh, sorry, I didn't even start it plotting at the time t equal to 0. So let me plot it from time t equal to 0 to say 100 or maybe even 50, just to make it slightly clearer. So I'm plotting only small parts of so that it's easier to see. Okay, here it is, yeah. So this is the observed component, which means that in addition to numerically knowing what the true trajectory is, which is the green line, I can also plot the observations on top of this, which is the dots that you see, the green dots, those are actually the observations. And then error bars to indicate how much is the observational error covariance. Yeah? And so you can see that, of course, the observations are not exactly on top of the trajectory, they are within the error bars and so on and so forth, blah, blah, blah. And now we can start interpreting. You can also see that the observed components actually converges to the true value slightly faster than the unobserved components, which I guess should be expected, right? If you're observing something, you have more information about it, so it should come closer to the truth faster. Okay, so that's one thing. You can find the error. Error is the difference between the known truth, which is only known in the case of these identical twin experiments. And so this is the difference between the truth, the trajectory, which was the true trajectory, and the ensemble. And the ensemble what? Ensemble mean. So you take the mean of the ensemble as an estimate of the truth and find the difference, that's the error. Of course, that's a three-dimensional object, and I can plot, for example, the norm of the error. The distance between the norm is just the distance between the error, between the truth and the mean of the ensemble, and that's what is plotted here. Do I need really 10,000? I don't know. Anyway, whatever, the time steps for now. So as we can see here, the error actually comes down quite significantly. It starts with an error of the order 10, right? Because we started with bias equal to 10. So the error is, can you give me an exact estimate for the error if the bias was equal to 3? Bias was equal to 10. The error is the distance between the truth and the mean of the ensemble. At time t equal to 0, I took the bias equal to 10. Bias basically was in each component, I simply added 10. So what's the distance? Louder, 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 louder. There's nothing like a wrong answer. So one obvious answer is 10. But you can see that it's not equal to 10, so it's gone. So what is it? And in fact, you can see what it is. How much is it? What's the estimate for the error? The blue line, here at time t equal to 0, what's roughly the value of the error? Sorry? Okay, 16, you said 16. So 16, 18, somewhere between 17 and 18, which is divided by 10. What is that number? Which is close to square root of 3. When you take norm of a point which is in every component 10 away from another point, it's 10 times square root of 3. It's exactly that, right? So anyway, so the other one is 20 times square root of 3, of course. And so about 34. So it starts with a very high error and very quickly comes down to something that then kind of remains statistically the same. You never get the error to exactly equal to 0, clearly. Okay, anyway, and then I'm plotting the covariance and so on, we'll talk about that later. So if you have already ran it and if you have qualitatively very different, so let's go through this. If you can run it and then maybe spend 10 minutes on that, something 5 minutes or something around that, is that fine? Sounds good. Have you, by the way, okay, so here is an experiment that we can try to do. One thing I did not explain to you is the following. I said forget about what this means. There is something called the perturbed observations, and I told you we'll discuss it later. So I think it's a good point to discuss right now. So what this is doing is as follows. The ensemble convolutional filter equation that I wrote down were exactly that equation, but let me write it again. XAI equal to XFI. So for each ensemble member, we are doing exactly the same thing. Plus K Y minus H XFI. That's what it's exactly that, but for each ensemble member. Instead of doing that, what the code is doing is adding a small perturbation to each of the observations. So for each ensemble member, the Y is not exactly Y. It's Y plus, so see, it's observation plus something small. And that small thing is, let's call it UI for now. Yeah, so that this object, the Y plus a perturbation, is what is called the ensemble of perturbed observation. So for each ensemble member, the observation, so to say, you get is slightly different from Y. It's not exactly Y. Why is that the case? I'll discuss that once we have run the code. So here is one thing that you can try to do. If you're running the code, try to run it by putting, so by the way, this is a multivariate normal distribution. The second component, the R there, is the covariance of that multivariate normal, which is observational error covariance. Instead of using that, put a 0. So for example, you can just do 0 multiplied by R. It will show up. Okay, so 0 times R, right? So now, essentially, this is like saying UI equal to 0, right? Because I'm setting the observational error covariance to be 0. That means that essentially the error is 0. And so this will correspond to this observation error going to 0. So run the code by changing this function to just this, which is multiply the R by 0. So firstly, run the code with R being there. See what you get. You should hopefully get something that's qualitatively similar. If it's not, then I'll walk around and see what it. So if you work together in teams of 2 or 3, that will be easier because more efficient. Rather than having to look at 40 laptops, I can look at only 20 or 10 or something. And then run it. Maybe make a copy and then run it. I don't know, if make a copy of the notebook, and so that you have the first set of results and the second set of results to compare. And if you run it with this R equal to 0, check what happens. Let's discuss that. Okay. So, yes.
You asked the question about the vector observation.
Yeah, I got it.
Yeah. Okay. So, should I now start spying on your computers? unless you are looking at your social media and so on, which you don't want to show me, in which case switch the window and
The police is coming.
the police is coming out. No, I'm just curious about whether you are getting something qualitatively very different. Somebody said that he is getting qualitatively different results, which
You should not warn people before you go. That should be a surprise.
that's what I was just saying, that please, if you're on your social media window, please switch your windows, go somewhere else, go on the window with a notebook. And so so somebody here said, you said it's qualitatively different. Okay, so what is the difference? It is not that different, is it? If you zoom into the initial part, you see that this is the line that's the true trajectory, and these are the two different ensembles, and they're. Oh, so he's just plotting shorter windows, I think. No, they're actually identical.
Yeah, but your graph is different. Very much different.
I was plotting a different variable, I think. I was plotting the x variable, the 0th component. This is, I think, probably the 3rd component. Or maybe, see, the thing is, it involves random number generation, which means that they will not be identical. The initial condition may be quite different. That's possible. I don't know what the initial condition is, for example.
It was this lines.
Sorry?
These lines was in the negative, like it was down to -5.
As I said, depending on the initial condition, the trajectory is different, right? So because the initial condition is chosen randomly, if the seed is different, for example, if something, or by the way, also the other thing is that each of you will have a different Python version. Random number generation will be slightly different in different Python versions. You will not get the same set of random numbers, and hence the trajectories may turn out to be different. But qualitatively, they will be hopefully similar results. Yeah.
So these are very different, these two ensembles. Means like
Wow.
stability
Is lost.
yeah.
Essentially, yes. So that can happen. So, okay. So here is somebody has an example of where stability is lost in the sense that the two ensembles, the magenta and cyan ensembles, kind of do this and eventually become separated. Why is, and this is after putting r equal to 0. Okay? So here is one possible result that may happen. Once you put, so I told you run the code with two different cases. One is with the observation perturbations, the ui being non-zero, and in the other case, multiply it by 0, so essentially the ui is equal to 0, and see what happens. So one possible result, so this is a potential pitfall, whether this is the outcome of u equal to 0 or not, that we need to discuss, but this is a possibility that the stability may be lost. Anybody else? Anything, any other outcome that you're seeing that is qualitatively different from what I showed? After running it with r equal to 0. By the way, also plot the errors. The code to plot the errors is also at the bottom. Right? So the stored ensembles, then eventually there is this x error, the error variables, and then you take the norm of them and plot the norm of the error. Yes. Oh, r equal to 0. Okay, so here is one more example. It looks qualitative. Do you want to describe what's the difference? What's one of the big qualitative differences? One is stability. So again, the two ensembles become distinct. So the stability is lost. What else? The spread is less. They almost look like a line. The spread is extremely small. The uncertainty is small. That means the precision is high. But on the other hand, the green trajectory, it's not on the screen now, and the ensemble are quite distinct. So it is highly precise, but what is not, so there were two words that I used to describe accuracy. So it's not accurate, but very precise. So that's what happens if you set the ensemble, the observation error covariance for this variable ui to be equal to 0. So let me run this and let's see what happens. Okay, so I will do this, generate an ensemble, run it with the UI equal to 0, do it here, do it once more, which is, okay, just for the sake of it, I'm not going to multiply it by 0, since anyway it's numerical, but by a small number, let's say 0.01. Rather than keeping it exactly 0, I will make it much smaller. So let's say 0.01, something, yeah? So now the UI variable will have a much smaller variance than in the first case that we ran. So let's see what that does. Okay, so that's my second. My first ensemble was with the UI equal to 0. The second ensemble is where UI is small. The variance of UI basically is small, right? And let's see what comes out. I have never run this before, so I have no idea what's going to come out. We will see what comes out. So the first, okay, so this is what many of you hopefully have seen by now. When you set R equal to 0, the ensemble variance decreases quite a lot, keeps going down, and eventually the ensemble is so sure of its own estimate because it's very precise, but it's highly inaccurate, but still continues to be highly inaccurate and highly precise. A terrible situation to be in, and this is what is typically called as as a divergence of the filter. Divergence because, why is this called divergence? So let's plot the next thing, which is, right, so here you can see that the two ensembles first is, so stability is lost. So the two ensembles separate from each other, and they also go away from the true trajectory. So it's neither stable, nor is it accurate, completely undesirable situation, right? Okay, so I'm not going to plot the second one, the third plot and so on. Let me just jump to the errors. So this is the error, and if I plot the error as a function of time, look at what this looks like. So, oops, sorry. It looks like this. So the error did go down initially for some time. That's what we should have expected. But eventually the errors started picking up, and the ensemble completely lost track of the filter, completely lost track of the truth. And the two filters completely lost track of each other. Yeah? So this is exactly what a extremely arrogant person would do. Very sure of yourself, but very far removed from reality. And so, okay, arrogant ensemble is a bad idea. So that's right. Okay. So this, by the way, was from the previous run when I had run this notebook previously. If the bottom of it has a code to calculate the ensemble covariances, and this was the plot of the covariance as a function of time. Actually, sorry, variances. So the variance of each of the three components, x, y, z, as a function of, no, sorry, I'm wrong. Sorry about this. These are not, okay, I messed up. These are not variances which are plotted. What is plotted is as follows. You have a 3x3 covariance matrix. The diagonal entries are the variances of each of the three variables x, y, and z. It's a positive symmetric, positive, in this case actually semi-definite matrix. It may have zero eigenvalues. We'll come to examples when it does have zero eigenvalues. And so it's a positive semi-definite matrix. I can calculate the eigenvalues. They will be all positive numbers, non-negative numbers, and that's what's being plotted. These are the three eigenvalues of the covariance matrix as a function of time. You can see that one of them, in fact, is very, very close to zero. So it is actually numerically positive semi-definite. It's not really positive definite anymore. But the other two eigenvalues are quite close to being non-zero, and okay, they fluctuate and so on and so forth. That basically means the variance is fluctuating, which is fine. It will do that. Now, this was from the previous case when the UI was not equal to 0. So this was from my previous run when I had plotted this. And now let's see what I don't know what's going to come out with the case of oops. They're almost all very close to 0. So in fact, this is a bad plot. I should do semi-log y. And the semi-log plot looks like this, which means, look at the eigenvalues. 10 to minus 2, 10 to minus 4, 10 to minus 10. The ensemble's own estimated uncertainty is no higher than 10 to minus 2. That's the highest eigenvalue, which is terrible. So it is, if you want to give an error estimate, if you want to give an uncertainty estimate along with your estimator, that is going to be of the order of 10 to minus 2. But the actual error, that is distance to the truth, is order 1. Right? Another sort of way to look at filter divergence. The uncertainty is tiny, the errors are very large. Bad situation. Yeah? Okay, so anyway. Now, in the remaining 25 minutes, I will explain what we just did. That is, what was this UI that was needed and why was it needed? So, suppose the UI is not present. So I'm going to start doing the computation assuming this to be equal to 0 for now. And we want to, one thing that happened as we saw, the covariance goes to 0, right? If the UI is not present, for example. Also, the error goes to, error becomes large, and that's a consequence of it that will come to later, but let's look at what the covariance. So how do you compute ensemble covariance of, so this is the I equal to 1, 2, up to n, and n is the ensemble size. How do you compute ensemble covariance of any quantity? So if I want to compute the forecast ensemble covariance, which is the ensemble represented by xif, I goes from 1 to n. What's the definition of ensemble covariance? So let me write it like this. So p hat f, the definition is the following object, 1 over square root, y square root, no square root. 1 over n minus 1 times the sum, I goes from 1 to n, of xi f minus x bar f times the ensemble minus the mean, its own transpose, sum over the whole ensemble, and that's the sample covariance. Ensemble covariance, sample covariance, and so on and so forth. If you haven't seen this definition, please go back and look up your basic statistics book that you used. If you have never taken a statistics course, find a statistics book. I would not suggest, if you have never seen this, then going to C.R. Rao to look up, because it's a heavy book, not an introductory book. But anyway, so that's a definition. That's a definition of a sample covariance. This is what we want to compute and understand what this is. Okay, so let's go through the steps. If I want to compute the analysis covariance, I need more blackboard space. So I want to keep this also. So let me erase this part. I will just indicate the steps, and you have the full weekend to finish that computation. I will be back on Tuesday, and I will ask you for that computation. So you're not getting off that easily. So here is the way to compute this, right? You want to compute this object. One simple, a schematic way by which this can be represented much more compactly and easily is as follows. Let's define a matrix called ZF. So this is going to be a n cross capital N matrix. So each column will be of length n. So that's a column vector. And each column vector is going to represent this object here. So each of the columns, I will indicate it by I, is equal to basically, and then divide by 1 over square root of n for ease of notation, times xif minus x bar f. Right? So this is n cross n matrix. Each column is that what is called, what is it called? Anomaly, deviation, something, whatever, I forget now. And same for ZA. So ZA will be defined exactly the same way for the analysis ensemble. And the P hat F, this is something you can verify, is basically equal to, as a matrix, is equal to ZA transpose. This was n cross n. This is also n cross n. Now I'm not going to say this n and that n. Okay, I can't anyway, whatever. So, right, so this whole matrix is dimension what we want it to be. Capital N has disappeared now. And that's what we want to compute for the analysis. If you want to do this for the analysis, we want to see what is the column vector. Let me erase this. So what is ZAI, the ith column? It's the ith column of the xia minus x bar a. So if you take the mean of this, mean across what? Across I. So sum over I divided by n, capital N. Can I, on the fly, change this to a P for now, so that we don't confuse the dimension n and the ensemble size n? So the ensemble size will be called P for now, just to, so that I don't have to say capital N all the time. Yeah? Okay, so if you do the sum over I goes from 1 to P divided by P, that gives the ensemble mean. Applied here, applied here, applied here, applied here. You know that mean is a linear operation, taking mean is a linear operation, which means that the mean of this and will follow equation that will look exactly like this. So convince yourself that this is the equation for the mean. X bar A will be related to X bar F by this equation. Convince yourself that that's true. Now you subtract xia from x bar a. The right hand side also subtract. The first term is xif minus x bar f. That's what is in the columns of zf. In fact, actually, so maybe sorry, I skipped one step. An easier way to do this computation is to rewrite this equation in the following fashion. xai equal to identity minus kh xfi plus ky plus kui. I'm keeping the ui in the equation so that right now I'm kind of trying to neglect it, but if I want to write it like this, then this is the full equation, right? So when I subtract the mean, x bar, it will get multiplied by I minus kh. What will happen to this? This minus the same term in the mean equation, so that whole thing drops to 0. I will only be left with the kui, but I'm right now assuming that kui is equal to 0. So none of these terms will remain, and this will simply be I minus kh zf, the ith column. And if this equation is true column by column by column, then clearly I can just take away the I, and this is now equation for the whole matrix ZA. ZA equal to I minus kh times ZF. And once this is the case, what is P hat A? It's ZA, oh sorry, no, typo. Nobody pointed out the typo. PF hat is ZF for the forecast. and PA hat will be ZA, ZA transpose. Okay, there was a typo here. So this will be ZA, ZA transpose, which will be, take this matrix, its own transpose. When you take its own transpose, this times the transpose of the whole thing. And so it will be I, and if you are a bit confused, that is perfectly okay, but you can finish the computation later and convince yourself that this is true. And here is one little bit which now I'm trying to remember whether it was in your slides or not, which is that look at this equation here. Oh, I have the hats. Those are the sample values, right? Those are sample covariances. The true covariances in the Kalman filter are supposed to follow this equation. The analysis covariance is equal to I minus kh times the forecast covariance. That's the case for Kalman filter, which is what we want to get to. We got almost, but we want to have this extra bit which is unneeded. Here is a bit which I will not prove, but so show homework. Show that PA is equal to I minus KH, PF I minus KH, plus or minus, plus or minus, plus or minus, plus or minus, plus or minus. Plus. It should be plus, but okay, so that expression that's over here can actually also be written as this. This is just an identity. So this is just a mathematical identity. Using, if I don't remember this uses Sherman, Morrison, Woodbury formula or not, I forgot the proof. So if you ask me to prove it right now, I will not be able to do it. But I will have to sit down and think through it, and so I don't remember how to do it. But this is equal to that. And that's a mathematical identity. So what does this mean? That the ensemble analysis covariance that we obtain, if we do not have the KUI here, which is this object, is, well, it looks like this, exactly looks like this, but with an ensemble covariance sitting here, but without this additional bit, right? So I really should have a KRK transpose, but I do not have it. So this is what we have, which is basically that minus this bit. So this parenthesis, the square parenthesis, would have been the true correct for analysis covariance. And that's good. That would have been a good thing to have. But we don't have it. We are missing this little bit. So we are subtracting a little piece. Or rather, the other way to think about it is that, I don't have, this is just 0, right? Plus this minus that, so that's 0. So anyway, so forget the 0 for now. What I have is less than what I want by a small amount. And this statement is actually mathematically accurate in the following sense. These are matrices. So what do you mean by one matrix is less than the other matrix? Does it make sense? If you have a matrix A and if you have a matrix B, and I tell you that, oh, A is less than B, not a 1 by 1 matrix, higher dimension than 1 cross 1. Does it make sense? Somebody said no. Somebody said yes. Does it make sense or does it not make sense? If I have a matrix A, can I say that A is less than B? Is this meaningful? And this is more than 1 cross 1 matrix. Is it a meaningful concept for a matrix? No, no. Anybody else? Under what conditions can this actually be made meaningful? When the matrices are symmetric and then eigenvalues are real. And for now, we are only dealing with symmetric positive matrices. So these are all symmetric positive semi-definite matrices. So this statement can make sense if, for example, so if A and B both are symmetric matrices, and if A minus B, that's a useful object, that's also still symmetric, and if all the eigenvalues of A minus B are less than 0, I'm not going to write it down, too long a sentence. So I'll just write it as this is less than 0. What I mean is, all the eigenvalues of A minus B are less than 0, then this is the definition of A less than B for symmetric matrices. So for symmetric matrices, comparison makes sense. For matrices which are not symmetric or not positive definite and so on and so forth, actually you don't need positive definite, but anyway. So in these cases, we are dealing with symmetric matrices. So it does make sense. Is this symmetric? This little bit here? What's the transpose of this matrix? When you take the transpose, you go in reverse order and take the transpose of each of the pieces. K R K transpose will be K transpose R transpose K transpose. It is symmetric because R is symmetric. R is a error covariance matrix that is symmetric. So this is symmetric. So this is symmetric matrix. This, by the way, it's not obvious why this is symmetric. It's not easy to see that this is symmetric. You agree? That if I take a transpose, what do I get? PF transpose times the transpose of this. I don't know, is that the same as, but it happens to be symmetric. And in fact, one more typo that none of you noticed either, which is, look at what we wanted to do. We wanted to get Z8 transpose. This times its own transpose. The ZF transpose gave P hat F. This remained on the left-hand side. The transpose of it should sit on the right, and this should have been a transpose. Sorry about that. And the identity will be incorrect if I didn't have a transpose. Okay, so I need that without a transpose, the identity was wrong. So the transpose has to be there, otherwise it's not correct. Okay, so I missed the transpose. Sorry about that. I mentioned that this is equal to that, and now this is obviously symmetric. What's the transpose of this object? Transpose of that parenthesis, which is here on the left, times PF transpose, which is PF, transpose of that, which is exactly there, and so this form of PA is not obviously, it's not immediately obvious that this is symmetric, but when you prove that this is equal to that, then this becomes obviously symmetric. And so this form is actually easier to kind of see the properties of this matrix. Anyway, so what we are missing, so this is symmetric, this is symmetric. R is a positive definite matrix. In fact, R is just covariances, right? So they're all positive eigenvalues for sure. K transpose, that does not change the positivity. So this is a positive semi-definite matrix. So I'll leave it to you to prove that this matrix is positive semi-definite. Why semi-definite? Because it has 0 eigenvalues, and the question is, so prove that this is positive semi-definite, and part of the proof will be find the number of 0 eigenvalues. Yeah. What's the dimension of this matrix, by the way? K transpose is beta B n cross n, the dimension of the system, right? But it has 0 eigenvalues. How many? You can precisely tell how many 0 eigenvalues it has. So that's part of the, yeah, but anyway, so it has some 0 and some non-zero, some positive eigenvalues. It's a positive semi-definite matrix. And now we see that what we are missing, the missing bit is actually positive semi-definite, which means that this matrix is less than in the exact same sense as I mentioned here, than what is actually desirable. So that's the reason why when you do not add these kind of perturbations to the observations while doing ensemble Kalman filter, it underestimates the covariances. So basically this object is the sample covariance is an underestimation of the true covariance of the Kalman filter. If you do it consistently, every time step, every assimilation step, you are underestimating the covariance. And that's the reason for why the covariance just collapses to 0 or very, very small, not exactly 0, but very small. So it becomes very, very precise. If it becomes very precise, remember the interpretation that, okay, so here is one other way to write this equation. Oh, it's here, yeah. Oh. Analysis is a linear combination of forecast and observations. The weight given to the observations is k, the weight given to the forecast is I minus kh. If the analysis covariance, the PF, if the covariance goes to 0, becomes smaller and smaller, what will happen? Look at the formula for k. It's a bit tricky, but let's go through it. This is going to be a bit hand wavy. I will try to make it precise in the next lecture if possible, but anyway, this can be made mathematically. So if PF goes to 0, if the covariance is 0 or very small, what happens? In a way, in this sum, this term is very small. They just R inverse here. And then there is a PF, which is also small. So K, in some sense, K kind of becomes small. So think of it this as K going to 0. K is not a symmetric matrix, so I can't really, K going to 0 is not a mathematically precise statement, but it's approximately, at least, for example, you can put a parameter in front of PF, let's say multiply PF by delta, and then as delta goes to 0, K will actually go to a 0 matrix, right? If K goes to 0 in this equation, what happens? So again, I'm dealing with this case, the UI, this thing is absent. I have 5 more minutes. So when K goes to 0, that's gone. This is gone. So the forecast is analysis. Observations are neglected. And this is basically what's happening when I said the ensemble is like an arrogant person who does not take into account the observations of the real world and believes too much in itself, right? So that's basically exactly what was happening in this ensemble Kalman filter. Then that is the filter divergence. The filter diverges, goes on its own, and this is the origin of it. So what's the solution? The solution, so there are 3 solutions actually. One of the solutions, the other 2 I will talk about later, but is this. Suppose you add a random variable such that the covariance of UI is equal to R. So the thing which I didn't specify. So now keep it here and say that UI is normal with mean 0 and covariance R. So UI random variables have covariance which is actually equal to the observation error covariance R, which is what we started with. Remember the first simulation was with UIs, these additional observation perturbations being that. So what happens in this computation? What did I do? Okay, so what is ZA now? Remember how we got ZA from that equation over there, subtracting the mean. When you subtract the mean, that's the term which is the ZF term. KY cancelled after subtracting the mean. But if the UI is there, that will be present. So this will look like plus KUI. Now, when you take the transpose, so you take ZA transpose, what will we get? We basically will get the ensemble covariance of U's, the sample covariance of U's, but U's were random variables with covariance equal to R. So this term, its own transpose, K UI transpose, K transpose, something should be happening, right? There is a K transpose, something in between, which is UI transpose. UI transpose should be equal to R, sum over I goes from 1 to P, divided by square root of 1, P minus 1, and all that kind of stuff, should give eventually K transpose. And there will be a cross term which will be ZFI's UI transpose, and so on and so forth. So there will be a cross terms. The cross terms being 0 is like a mantra in all calculations, right? Whenever you're doing, say, quadratic computations, you do squares, something happens, quadratic, the cross terms are either set to 0 or so on. So anyway, so there will be cross terms. What happens to cross terms you can worry about and maybe tell me or ask me next week, for example. But you can see that in addition to getting I minus KH, PF transpose, I minus KH transpose, now we actually get K UI transpose by square root of M minus 1 and so on, which in fact is close to being R because these were random variables with covariance equal to R times K transpose and additional cross terms. So instead of having, so with the UI being non-zero, what we actually end up getting is, so this is, you get this term, plus there are cross terms. And basically the idea is that the cross terms are kind of, they don't have a sign definiteness. They are sometimes positive, sometimes negative, so on average they actually do cancel, and the cross terms are small or 0. So typically, what do you mean they are cross terms? It will be the UI ZF times UI transpose and so on, right? Those cross terms. So those are small, and then finally it turns out that this covariance is close to the what we need it to be, which is the true ensemble covariance, the analysis covariance of the ensemble Kalman, of the Kalman filter. So the ensemble Kalman filter can be made close to Kalman filter by using what is called now perturb observations. So the UI, Y was the true observation, Y plus UI are called perturb observations, and this is called a perturb observation or stochastic ensemble Kalman filter. If you do not want to introduce stochasticity, if you do not want to introduce noise in the observations, there are deterministic versions which will have to wait after the T.
One point to add here is that the filter divergence which he is speaking about, in real world data assimilation, what happens is that your background becomes more and more confident, and over a period, the observations will not be taken in because the background variance is going to be less and less, and background become more confident and less observations are being used. So that's the effect in the real world data assimilation because of filter divergence. Thank you.